Okay, students. In this video, we're going to go over some notes here on Newton's laws of motion. So one of the first things that we're going to state is when we're talking about forces, we have to be able to accurately draw the scenario of the forces that are acting on a given object. I think in our next lesson, we're going to learn that there are a variety of different forces that can act on an object, such as things like the normal force, the force of gravity, friction, or an applied force. But in this lesson, all we're really going to be concerned with is being able to draw these forces in something that is known as a free body diagram. So a lot of times we'll draw an object regardless of what it is, just like this. So right, a bus, there it is. A plane, there it is. A cow, there it is. Then we represent our forces as vectors being drawn on the object. A force is a vector, something that has both size and magnitude, or I'm sorry, size and direction. So we can represent it with a vector. Now, one of the important things here, and this is kind of nitpicky, I guess, for Regents level physics, is that the vectors have to be touching the object. So I often put a center of mass point in my object and then draw my vectors accordingly. So maybe I have a force here of, say, 10 newtons to the right, and maybe a force of, say, 6 newtons to the left. There's a accurate free body diagram. And so we're going to be drawing these diagrams a lot throughout this lesson. So let's talk about Newton's laws of motion. There's 3 of them, right? Newton's first law says that an object at rest remains at rest, and an object in motion remains in motion unless acted upon by some external force, right? So if I have a cow and it's just sitting here, that cow is going to stay at rest until someone comes along and pushes it and applies a force. Then you know that that cow will begin to move, hopefully. Now, why is it that an object at rest remains at rest? Or I guess we should also say an object in motion remains in motion. Let's talk about that one, right? If I were, let's just say I rolled a ball, right? Here I am, and I roll a ball, okay, and that ball starts rolling, you know that it's in motion. Is it going to stay in motion? Well, no, it's eventually going to come to rest, right? Its velocity is going to be 0, and the question is why? Well, there's a force acting on it here. In reality, there is the force of friction that slows it down. So the force of friction is acting upon it. It's the net external force causing it to slow down. But imagine if I were out in space, okay, this is me in space, and I threw a ball. That ball would continue to move on and on and on in a straight line forever and ever and ever and ever, and it would never stop until maybe it encountered some object that exerted a force on it. Like maybe here's, I don't know, we'll say Saturn. Here's Saturn with its rings, and the gravitational pull of Saturn began to cause it to orbit Saturn. So why does this happen? Well, the key idea here is that objects with mass have something known as inertia. And inertia can be defined as an object's ability to resist a change in motion or to resist an acceleration. Things want to keep doing what they're doing. They don't want to change. And the reason why is because of the object's inertia. And inertia is directly proportional to an object's mass. So that means the more mass an object has, the more inertia it has. The harder it is to change its motion. So if you look at these two sort of scenarios here, here's just an empty bucket hanging and an empty bucket filled with sand. This sand-filled bucket has more inertia, right? More inertia because it has more mass. And so this is much harder to get moving, right? If you could easily come over and push this bucket and the bucket would swing, but this one would be much more difficult to get to move. On the flip side, it would also be harder to stop its motion. Imagine if I pulled this bucket back and then let it go and your face was right here. Well, your face is not going to stop that bucket. It's going to just plow through it and you're going to have a broken nose. Whereas this one, right, if you put your face here and I pulled it back and let it go, you might be able to stop the motion because of less inertia. Now, when we talk about Newton's first law, we're talking about objects that are either at rest or moving with a constant velocity, right? An object in motion will stay in motion. It's just going to chug along at a constant velocity. An object at rest will stay at rest. This happens when an object is in equilibrium. So that's that key word here, equilibrium. We say Newton's first law states one condition has to be true for equilibrium. The net force acting on a body in equilibrium must equal 0. So if you look here, right, here's a scale. There's 100, we'll say, newtons of force pulling down on this side. And here we also have 50 and 50, 100 newtons pulling down. So this point is in equilibrium. This is better pictured in these free body diagrams right here. In our first free body diagram, if you look, we combine our horizontal forces, 30 newtons to the right and 30 newtons to the left, gives us, for the horizontal net force, 30 newtons to the right plus 30 newtons to the left, 0. And in the vertical direction, if we look at our vertical forces, we have 50 newtons up and 50 newtons down, which is also a net force of 0. So this object is in equilibrium. If it's at rest, it's going to stay at rest, and if it's moving, it's going to continue moving at constant velocity. Same thing here with the second diagram, okay? These are objects that are in equilibrium because the overall or net force on the object is equal to 0. Now, we can only combine horizontal forces directly together, and we can only combine vertical forces directly together, which is exactly what we showed here in these diagrams, okay? When I'm looking at this first diagram, I'm only looking in the horizontal direction. 30 minus 30 is 0, and I'm looking in the vertical direction. 50 minus 50 is 0. For forces that are in 2 dimensions, that's going to require a use of vectors for their combination, all right? So if we have forces that are in 2 dimensions, like this vector, which that I guess we'll say points up into the right, we have to use vectors to combine them or add them. Now, when the net force acting on an object, well, actually, let's go back and look at just a small example of this. So imagine if I had, we'll say, a force of 3 newtons this way and a force of 4 newtons this way. You might ask, what is the net force acting on this object? Well, to get the net force here, we can't combine these two, so we don't know if this object is in equilibrium, but I can combine them by using vectors. 3 newtons, I'll place them tip to tail, 4 newtons. The resultant vector now points up and to the right, and we'll say that it has a magnitude 3, 4 of 5 newtons, right? That's a Pythagorean triple, 5 newtons. So you're going to use a squared plus b squared is equal to c squared here to solve for that resultant. Okay, so one of the concepts that you have to know in regards to Newton's first law is the equilibrant force. When the net force acting on an object is 0, we said that the object is in equilibrium. But if it's not in equilibrium, the equilibrant force is the single additional force that you can add that will produce equilibrium. So if you look here, right, a simple example, a net force of 55 newtons acts due west. So we'll say 55 newtons. Okay, so clearly this is not in equilibrium, right? There's nothing counteracting this net force. What is the equilibrant force? What is the single added force that places this into equilibrium? Well, it's going to be 55 newtons east is the equilibrant. So it's pretty easy when it's in 1 dimension, right? 1 dimension, right? If I say the net force is this, 10 newtons up, well, then the thing that's going to place this in equilibrium is 10 newtons down. Not too bad. But when we're in 2 dimensions, it becomes a little bit more challenging, right? So here we have it in 2 dimensions. What is the equilibrant force on the diagram below? Well, first we should figure out what the net force is, right? I have 20 newtons up and I have 20 newtons to the right. So clearly this is not in equilibrium. So I'm going to draw my vectors tip to tail, 20 newtons and 20 newtons. And so I can combine these by using the Pythagorean theorem. Right? So a squared plus b squared is equal to c squared. And so if we look here, this is going to be 20 newtons squared plus 20 newtons squared is equal to c squared. Well, 20 squared is 400, so I get 400 plus 400 is equal to c squared. So I take the square root of 800, and that tells me that c, the magnitude of the resultant force, is 28.3 newtons. So I can combine these two and say, okay, this force sort of points up this way with a magnitude of 28.3 newtons. So then the question is, well, what's the equilibrant? Well, the equilibrant has to be the force opposite that. So it's going to be 28.3 newtons going down this way. All right. Now you may say, oh, hey, don't we need an angle here to indicate the direction? And you're absolutely correct. Okay, we got to be a little bit more specific here with the direction. So I'm going to name my angle theta. Okay, and so I'll say the tangent of theta is opposite over adjacent. And I get the tangent of theta is 20 newtons over 20 newtons, which is just 1, right? So theta is equal to the inverse tangent of 1. And so if I do the second tangent of 1, I get a nice angle of 45 degrees. So this angle here is 45 degrees. And if you remember some geometry, it tells us that this angle right here is also 45 degrees. So I guess the equilibrant might be 28.3 newtons